There has not been much focus on the impacts of clay's chemistry on the fracking process. The target of this video is to highlight the crucial importance of this topic, how it affects the efficiency of the fracking process, and how huge is the window to improve this process if the drilling and fracking water-based fluids were designed properly. One of the technology leaders in the fracking industry is George King, who has a vast experience in this field. He highlighted the critical technology gaps in the clay's chemical side, and their impacts on the efficiency of the fracking process, in his presentation held in the Hydraulic Fracturing Symposium at Texas Tech in 2013. Next are his important points with our comments.
Nature does a beautiful job of creating fractures a lot better than we do. We just enhance some of the ones next to the wellbore. The reason these natural fractures are so incredibly important, and this work was done by Julia Gale, Texas Bureau of Economic Geology. What she found was these fractures can actually open up at much lower pressure than it takes to actually fracture the rock itself. That is a really good thing because it helps generate a whole lot more contact and surface area without having to use an excessive amount of fluid or create huge fractures. We're just reopening the natural fractures in many cases. This is actually more effective than planar fracturing or opening the large fractures like we did in tight gas sands. We depend on a lot of things. Natural fractures are good, but we also have to have a lot of contact area. And when Mother Nature gives us some good naturally fractured reservoirs, we can open those natural fractures, keep all of our fluids in zone, and it's very effective after that. Notice here that in several cases, only a few of these zones are actually flowing. This is the other piece of technology I'd like to improve. Where do you put the frac? Too many companies are just taking 500 feet or 300 feet for a frac job and saying, okay, we're going to just divide this up mathematically and put a frac here, 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 and here, 50 to 100 feet apart. That's not efficient because many of these fracs don't work. They don't flow hydrocarbon back. The reason why, go back to that slide I showed you, not all of that shale is productive. May have oil and gas, but if it doesn't have the natural fracture system in to flow, your frac is not going to be productive.
These high-importance natural fractures were created due to a chemical process in clays. This process is called the elitization of smectite and kaolinite clay minerals. Additionally, and due to this chemical process, part of the oil or gas was expelled by pressure from the shale pore space, and then migrated by buoyancy through these natural fracture systems to the porous and permeable host rocks, creating the conventional reservoirs. As a result also of this chemical process, and for specific reasons, the shale play shows adductal behavior, which protects the conventional reservoirs from the impacts of the tectonic movements. Another product of this chemical process is quartz, which explains the coexistence of high quartz contents with these natural fracture systems in the potential unconventional plays. This demonstrates how crucial is the role of clay's chemistry in the creation of the unconventional and conventional reservoirs, and to the sustainability of these natural and induced fracture systems. The importance of the clay's chemistry during the well's life cycle comes from the facts that clays are the soft components of shale, and clays have high affinity and reactivity with water, which is the dominant constituent of drilling and fracking fluids, being utilized in the industry for environmental and industrial reasons. So, shale is a degradable rock. This degradation can take place any time during the well's life cycle, starting from drilling and ending with hydraulic fracturing. This degradation is irreversible.
Now, what's holding the water in, and basically if you look at this, we're putting down around 4 to 5 million gallons of water. This is the approximate return that we get back to the surface for the various shales that are out there. You get more coming back out of a sandstone, less coming back out of a shale because the water is bound. Shales are undersaturated with respect to water. They'll grab the water and hold on to it. So we don't have as much coming back. We need some help on the chemical side making this work. If we get good help on the chemical side, we can cut down the volume of water and the time that it takes us to get any of these things. We may be even able to do a lot less wells. So there is some benefit to working on this. And I know I'm talking a lot about technology gaps. There are still some technology gaps. There's some places for good work. What we're dealing with here, and this is the concrete beneath your feet, and this is the shale permeability. So the shale is about 2 orders of magnitudes less permeable than the concrete floor. We got to get more fluids coming up. Give you an idea of what's happening. This is the Eagle Ford down in South Texas. In places it's 80 to 100 miles wide, a few hundred miles long. And I have thickness and other types of things up there. There's an oil reservoir in green right here, a light oil reservoir or heavy gas liquids here, and a gas reservoir down on bottom. Not much drilling in this area, but as you look at the 10% best wells in the field, which are in yellow, a little hard to see, those are mostly in that area where you can recover gas and gas liquids. The worst 10% of the wells in blue are usually in this heavier oil area. So we're not effectively getting that out. There again, we're making headway in that. That's something that science is going to have to help us with. All right, here's what we're fighting against right here. This is a Barnett. And that's only one sample, so my population control isn't very good. But when you look at the pore throat radius coming across here, you need big pores to flow oil. What have we got in the Barnett? 95% of our pores are in micrometers down here into the 00 range, 0.00 something. That makes it very difficult to flow liquids in those areas. So we need better methods.
It is in fact so crucial to have a comprehensive methodology to take care of the shale during the whole well's life cycle. A specific strategy should be set up in designing the water-based drilling and fracking fluids for each shale play, to avoid any deterioration both to these natural and induced fractures systems. These designs should consider all the chemical and physical related shale modes of failure, the shale core's X-ray diffraction analysis, the clay's diageneses, the clay's transformation reactions and other factors. To have a configuration of a continuous reservoir out of the unconventional play, and the best oil or gas production, we need to maintain the sustainability and interconnectivity of these natural and induced fractures nets. We need to consider that with shale degradations and the utilization of a high quantities of proppants, the tolerance in the space available for the flow of oil or gas through these fractures is very critical and small. Keeping in mind that the chemically related shale degradations are time dependent, and that the gas or oil shows recorded during drilling might not necessarily last even for few hours, due to this phenomenon of chemically related shale degradations. Additionally, if the drilling and fracking fluids are not designed properly, specific drilling and fracking water-based fluids ingredients have negative impacts on the shale pore throat radius, leading to an effective restriction to the flow of the oil molecules through these throats, and hence to the production of oil. Most of the large volumes of water utilized in fracking is kept in clays after the fracking process, leading to an effective damage to the unconventional reservoir, and loss of oil and gas resources. From the well's construction side, the improperly designed drilling fluids create effective chemically related increases in hole size against shale sections, which effectively deteriorates the casing cement's bond strengths, and hence dramatically reduce the well's integrity. This comes in addition to the relevant drilling problems and the associated loss of time and funds. All of these chemistry-related clays factors have negative impacts on the efficiency and production of the unconventional plays, and can even lead to the abandonment of parts or all of these plays. Taking care of the shale with a strategic and comprehensive methodology prepares brittle shale for the fracking process, and hence cuts the volumes of the fracking water and the water kept in shale effectively, yielding positive impacts on the environment challenges, well cost, water sourcing challenges, wastewater treatment logistics and cost, induced seismicity issues, and positive impacts on the recoverable oil and gas from shale. Accordingly, the scientific approaches in the field of clays chemistry give practical, cost-effective, and environmentally friendly solutions, delivering higher quality and integrity wells. No special products are utilized.